Principles of Bioproduct Separation, Module 10, Precipitation, Segment 4. With me, Yusuf from School of Life Sciences and Technology, Institut Teknologi Bandung. We have previously discussed about precipitation with a non-solvent, precipitation with salts, and precipitation with temperature. In this segment, we will discuss about large-scale precipitation. By large scale, it does not necessarily mean processes which produce tons or even kilograms. Rather, we mean processes which are 10 times larger than existing laboratory methods. In other words, this segment concerns with process scale-up. Large-scale precipitations are subject to the same equilibrium concerns as their small-scale parallels. For example, the solubility of a particular solute in a large-scale process is no different than that in a small-scale process. What can change in the large-scale process is the kinetics. We want the kinetics to be the same. We want to select those large-scale conditions which give this same precipitate. To see this, we idealize precipitation as a six-step mechanism. First, initial mixing. The feed containing the solute is mixed with a non-solvent or salt. Second, nucleation. Small seeds appear and precipitation begins. Third, diffusion, limited growth. The precipitate grows by diffusion. Fourth, flow-influenced growth. Further growth is aided by mixing. Fifth, flocculation. Colloidal particles segregate into larger flocks. And sixth, centrifugation. The flocks can be separated by centrifugation. Initial mixing. The time required to produce such homogeneity can be estimated using equation 8. The size of these eddies can in turn be estimated using equation 9. Nucleation is the step where small particles appear and begin to grow. In organic systems, nucleation can be slow and supersaturation can persist for long periods. However, in the colloidal systems, which are the focus here, this process is effectively instantaneous. Diffusion, limited growth. After nucleation, the precipitated particles grow as dissolved solute diffuses to them from the surrounding solution. This growth is usually found to be a second-order process as shown in equation 10. The rate constant is a function of the diffusion coefficient as shown in equation 11. Equation 10 can be easily integrated to give equation 12. Equation 12 can be rewritten in terms of molecular weight by using a mass balance as shown in equation 13. Combining equation 12 and equation 13 results in equation 14. Flow-influenced growth. Growth usually involves collisions between species which are swept together by mixing. Growth in this region obeys second-order kinetics as shown in equation 15. The rate constant is now given by equation 16. The quantity in the square brackets represent the square of the average velocity gradients caused by the mixing. Volume fraction of the solids can be calculated using equation 17. Equation 15 and equation 16 can be written in terms of the volume fraction of solute as shown in equation 18. Upon integration, change in particle concentration in the flow-dominated regime follows first-order kinetics and shows an exponential decay as shown in equation 19. Flocculation. The final step is the flocculation or agglomeration of existing precipitates. Experimental studies of this step are essential, for no existing theory can make accurate initial estimates. The high flow used to grow smaller particles can destroy the larger flocks, so that this step is sometimes carried out in an unstirred tank where the precipitate ages. Modest curing may strengthen the flux. In addition, synthetic polyelectrolytes can sometimes aid flocculation but later has to be removed. For a better visualization about precipitation, students may want to check these videos on YouTube for a better understanding. Until then, I am Yusuf from Institut Teknologi Bandung.